Let's start by quickly reviewing the development of the Hertzsprung-Russell diagram. Remember that in the early 20th century, two astronomers, one in Denmark, Einar Hertzsprung, and one in America, Henry Norris Russell, were looking for some way to determine the absolute magnitude of stars so that they could compare that to the apparent magnitude and use that to figure out the distance, something other than parallax to determine distances to stars. And so they compared the surface temperatures or stellar classes, which give us the same information, and the absolute magnitude or luminosity of the stars. Today in the modern Hertzsprung-Russell diagram, we include all of these properties because they represent the same thing. And if you remember then, we have on our y-axis the luminosity on one side, the absolute magnitude on the other. The luminosity is in solar luminosities. So if we put the sun on, obviously the sun has one solar luminosity, and that corresponds to an absolute magnitude of about +5. Turns out that stars range from about 1,000,000 times as energetic as the sun, that's a -10 absolute magnitude, down to about 1/10,000th as energetic as the sun, and that's an absolute magnitude of about +15. So we have these, we can fill in the remainder of these axes. On the x-axis, we can put the temperature from over 30,000 Kelvin down to about 2,000 Kelvin, and the corresponding spectral classes from the O-class stars that are 30,000 Kelvin or over, all the way down to the M-class stars that are between about 3,500 and 2,000 Kelvin. And if you remember, what Hertzsprung and Russell were sort of expecting to find was that there would be a direct relationship, that the hotter the star, the more luminous, more energetic the star is. So they were expecting something that would look like this. And if you remember, they found this direct relationship, and that represented the main sequence, even though it was a band rather than just a straight line. But there was much more to it that gave us clues about the lifetime of stars. And we can see that if we start doing what Hertzsprung and Russell did. They measured distances to stars that were close enough to use parallax. From that, they could determine the absolute magnitude of the stars or their luminosity. Using spectroscopy, they determined the temperature or spectral class of the star, and then they started to graph them. So the sun has a temperature of 5,800 Kelvin, a surface temperature, an absolute magnitude of 4.8, and that puts it about here on the HR diagram. Rigel, on the other hand, remember the blue supergiant in Orion, is a spectral class B8 that makes it much hotter than the sun, and it has an absolute magnitude of -6.7, which will put it up here, and that's pretty much what we expect to find so far. But then we go to a star like Antares. It's M1 spectral class, which means it's low temperature, and we would expect it then to be somewhere down here. And yet it has a luminosity of 65,000 solar luminosities, 65,000 times as energetic as the sun, which puts it up here. Low temperature, but high luminosity. That's surprising. We do this with other stars, like little HIP 12961, also a pretty cool star like our star over here, but in this case it has a luminosity only 1/10 of the sun. And if we keep doing this with Sirius, we discover something strange, that some of these stars just don't fit the pattern we were expecting. Like Sirius B is very, very hot, and yet it's very, very dim. So it goes down here on the HR diagram. And as we keep adding stars, what we discover is that we do have this direct relationship that we were expecting as the main sequence, but we also discover that there are stars that don't fit that sort of direct relationship. In fact, once we've plotted a whole lot of stars, we discover that they're basically different regions on the HR diagram. There's this region here, there's a region over here, there's a whole band across the top here, and then we have this group of stars way down here that are high temperature but low luminosity. So we can actually name, astronomers have named each of these regions. We've already met the main sequence that does follow that expected relationship where temperature is directly proportional to luminosity. The higher the temperature, the higher the luminosity. The lower the temperature, the lower the luminosity. And so the band goes from the top left to the top right. On the main sequence at the very bottom, the stars there are called red dwarfs. Because they're a cool red color, and they're also very, very small. That's why they're so dim, because they're very small and low temperature. Overlapping at the top end of the main sequence, there are a group of stars that are called blue giants. They're not on the main sequence, but they share similar temperatures. We're not going to say too much about the blue giants. Across the top of the HR diagram, there's a strange band here that's horizontal. And remember, when we were talking about graphs, that means there's no relationship here. The blue giants, the blue supergiants are much, much hotter than the red supergiants, and yet they're about the same luminosity. They're higher temperature, but that doesn't seem to relate to the luminosity. Lower down, in between the red dwarfs and the red supergiants, we have a group of stars called the red giants that are the same temperature as the red dwarfs, but much more luminous, and the same temperature as the red supergiants, but much less luminous. And then down here, this strange group here, they're very, very hot. In fact, they're white hot, but they're very dim, which tells us they must be very small, and so we call them white dwarfs. And so we can actually tell something about the size of these stars, because the biggest stars here must be the red supergiants. Why? Because they're amongst the most luminous stars, and yet having very low temperatures, they must have really, really, really big sizes to give off all that energy at low temperatures. So they must be much bigger than the blue supergiants. The red giants are the same temperature as the red supergiants, but not as luminous, so they must be smaller. And the red dwarfs at the same temperature must be really, really small to be so dim. And the white dwarfs, being such high temperature but such low luminosity, they must also be very, very small.